Good morning to you all, or good afternoon, depending on your time zone. You're all very welcome to today's webinar on sample size calculation featuring nQuery Advisor's most recent improvements. My name is Eoghan Murphy. I'm a statistician with Statistical Solutions. And before we begin, there are just some technical details on the webinar itself that we'd like to go through. Firstly, on the screen size, if any of you find that the screen is maybe too small or too large, you can adjust the size of the screen by clicking on the drop-down arrow at the bottom right of your screen. Also, if you have any questions, be that on the webinar itself or indeed on sample size in general, then there is a text box to the right of your screen in which you can input your questions. Now, we are very fortunate today in that we have a very experienced statistician in Andrew Grannell sitting in on today's webinar, and Andrew has kindly offered to answer any questions that you may have on today's webinar or, of course, indeed on sample size in general. Now, questions will be answered in rotation, so if your question is not answered during this webinar, then you will receive an email within 24 hours of the webinar ending, which will give you an answer to your question. Okay, just go through a quick outline of what we'll be going through today in today's webinar. We'll begin with just giving a brief overview of nQuery Advisor. We then go on to speak about power analysis. This is going through a definition of power, the reasons for a power analysis, and the steps you should take in conducting your power analysis. I'll then go through two worked examples using nQuery Advisor, one to calculate power and one to calculate sample size. We'll then move on to speak about nTerm, again just a brief overview of nTerm, and then we'll speak about group sequential trials, firstly giving a definition of group sequential trials, and speak about the benefits of using a group sequential trial. I'll then, of course, give a worked example of calculating sample size using nTerm. There'll be time then at the end for any questions or comments that you may have. Okay, let's give a brief overview of nQuery. nQuery was designed by Janet Elishoff. She's a professional statistician with many years' experience in study design. The first version was released in 1995, and including nTerm, there's been, on average, a new version every 2 years. Now, nQuery's Advisor is designed so that researchers can compute appropriate sample sizes easily. In nQuery itself, there are also assistants which helps you to provide the standard deviation and effect size information that are required for your power analysis. Now, so power analysis. Well, what is power? The power of a study reflects the probability that study will be able to detect a true effect of a specified size. So that is, power is the probability of rejecting the null hypothesis when it is in fact false. So why should I do a power analysis, you might ask? Well, the first benefit of doing a power analysis is that a power calculation not only estimates how many participants you need, but also how many you don't need. So how is this a benefit? Well, a study which is too large could be a waste of resources and could expose more participants than necessary to any related risk with your study. Similarly, a study which is too small could be considered unethical because exposing human subjects or lab animals to the possible risks associated with research is only justifiable if there is a realistic chance that the study will yield useful information. Another benefit of doing a power analysis is that it helps guide you in making adjustments to your study. So that is, it can help guide you on where to tweak your study in order to increase power without increasing your required sample size. So another benefit of power analysis is that many published studies have very low power and are bad sources for basing your sample size on. So if you were to base your sample size for your study on a similar study, there is no guarantee that your study will have sufficient power at the end of it. So to give an example, in Cohen's power analysis of the Journal of Abnormal and Social Psychology, he concluded that over half of the published studies were insufficiently powered to result in statistical significance for the main hypothesis. So it is vitally important that you carry out your own power analysis, which leads me on to my next point, with that an appropriate sample size is crucial to arrive at valid conclusions. The biggest benefit of doing these calculations is so as not to waste years and potentially thousands of euro in pursuing an impossible analysis. For example, if your power analysis indicates that you need 1,000 subjects to find significant results but you were limited to 50, then you simply you don't do that study. It'll be too underpowered. And finally, a power analysis is just a part of doing good research. Now, so the next thing you ask is, how do I determine an appropriate sample size for my study? Well, we look at this as being a 6-step process. The first being that you formulate your study. So here you detail your study design, you choose the outcome summary, and you specify the analysis method. The second step then is to specify your analysis parameters. So here you specify your test significance, whether it's a 1- or 2-sided test you're looking at, and what exactly it is you're looking for from your analysis. The third step then is to specify your effect size for your test. For example, you might want to specify the mean difference which is expected or which is important to detect. And then the fourth step then is, once you have all this information, you can then calculate whether it's sample size or your power. And the fifth step then, the sensitivity analysis. Here you compute your sample size or power from multiple scenarios. This will help guide you in making adjustments later to your study. And finally, you choose your sample size and write your statement. Okay, so for our first example, what I'll be doing is calculating power using nQuery Advisor. So in this example, we're looking at patients suffering from neutropenia. Now, neutropenia occurs after chemotherapy when the number of white blood cells decreases below a fixed cutoff. So the study plan here is to compare a new therapy to reduce the mean number of days of neutropenia with the placebo. So here, each patient will get the new therapy during one chemotherapy cycle and the placebo during another chemotherapy cycle. You can see this design here illustrated on this slide. So for this example, we're looking at a 2x2 crossover study. We're comparing a new mean with the placebo, and our question is, will 30 patients provide adequate power to detect a drop of 3 days? Now, a previous study reported an average of 8 days for controls, and from a pilot study we know that the standard deviation is 5.2. So in this example we're using a 5% level of significance, a 2-sided t-test, which is appropriate for a crossover design. So we now open nQuery Advisor to do our test. Now, there are quite a large number of tests in nQuery, so what we have here is we have a study goal and design window to help us narrow down our search for a test that's appropriate for our study quickly. So we're looking at means in our study. We're looking at 2 groups, and it's looking at a test. Now we're looking at a 2x2 crossover design, so we go down to the list, and at the bottom of the list here is a 2x2 crossover design. So you select OK, and this opens up the table for our test. Now, so you enter our values, so your test significance level of 5%, 2-sided test. Here we have treatment 1 and treatment 2, which is our placebo and our new therapy. So we edit our row names. So for treatment 1 we'll enter placebo, and for treatment 2 we'll enter new therapy. We update our table row names. So we now have placebo mean and new therapy mean. Now the placebo reported 8 days on average, so we enter 8. And our new therapy we expect to be 3 days better, so it's enter 5. So this again gives us our difference in means of mu1 versus minus mu2, which is 3. Now for this crossover design, we must enter either an estimate of the square root of the mean squared error from the crossover ANOVA or an estimate of the standard deviation of differences. Once you've inputted one, nQuery will automatically compute the other for you. So in this example, the standard deviation of differences was estimated to be 5.2 from our pilot study. So we enter 5.2 here, and nQuery automatically computes our crossover ANOVA square root mean squared error. Now, to calculate standard deviation of differences from other information, there's an assistant within nQuery, which I'll briefly go through now, to estimate your standard deviation. Here, depending on which information you have, you can then nQuery will estimate the standard deviation for you. So for example, if you had a certain amount of x values you had, you can then enter these here, and nQuery will calculate the standard deviation for you. Now, so back to our test. The total sample size that which we planned for our study was 30, so in our n per sequence group we'll enter 15. This gives us a power of 86%. Now, so the next step here is to run our sensitivity analysis for the fifth step. So for our sensitivity analysis, we're looking to see how changes in the new therapy will impact on power. So here we'll just do edit, specify multi-factor table for our sensitivity analysis. At 5% level, we'll maintain this for each save row. The new therapy means, so we want to look at how, as I say, how changes in the new therapy will impact on power. So we'll enter in a few different values for the new therapy. The save row. Okay, as you see, it automatically fills in now for you for each column. Now we want to keep our standard deviation the same, so you just click fill right. And as I say, we're limited in our sample size which you can have, so we'll keep this the same as well, so we'll fill right here as well. So you can see the impact this has on power. The power for when there's a large effect size, that is, there's a large difference between the means. When the new therapy mean is 4, giving you a difference of 4, that the power is, for the same sample size, the power is 98%, which is extremely high. But then you see as the difference in means decreases, as the difference in means gets smaller, as the effect size essentially gets smaller, how drastic an impact this has on your power, even for the same sample size. So what we're going to do now is we want to plot our power versus sample size. So we want to do this for column 1. So you click the button here for plot power versus sample size. So you can see here that up to a sample size of approximately 14, we get approximately 80% power. And then it's not until we get to a sample size of 20 before we see 90% power. See, the additional benefit of sample size decreases as it goes up in sample size. Okay, so once we're happy with our power, we can then generate a statement. So again, we select the column which you'd like to see a statement for. So you click statement. This gives us a statement detailing the test and the power associated with it. So here it says, when the sample size in each sequence group is 15, a 2x2 crossover design will have 86% power to detect a difference in means of 3. Now if you want to store this statement, you just click store, and it drops down here for you. So then if you want to, you can have print options, and you can select which you want to see print, and this will print out in a Word document for you. Okay, that's our example, our first example on calculating power using nQuery Advisor. We'll now look at an example of calculating sample size using nQuery Advisor. So we're looking at a non-inferiority for 2 exponential survival curves for this example. In this example, we'll be looking at survival patients with cancer. Now, many cancer drugs which are effective in prolonging survival put patients at considerable risk for serious adverse events. So a new drug with an improved safety profile would be of interest, even if it did not increase survival, so long as survival is not decreased in comparison with the standard. So for this example, suppose that the standard drug results in a median survival of 12 months, and the new drug might be considered to be not inferior as long as the median survival was not lower than, we'll say, 10 months. Now this is a non-inferiority trial with a survival outcome. The study plan has an accrual period of 18 months and a maximum follow-up time of 24 months. So that is, the total trial length will be 24 months. Those first to enter will be followed for 24 months, and those entered at the end of 18 months accrual period will be followed only for 6 months. Okay, so once again we'll open up nQuery Advisor. We can minimize this test. So it's a survival test. Again, 2 groups. And we're looking at equivalence. So we're looking at non-inferiority test for 2 exponential curves. Now this is essentially a one-sided equivalence test for non-inferiorities. So click equivalence. Okay, so here we enter 0.25. Length of our accrual period is 18, and the maximum follow-up is 24. Now for the common exponential dropout rate D, we'll enter 0. So what we're saying in this case is that we do not expect loss to follow-up for the survival outcome. So again, press enter. Now, we must specify the exponential survival parameter for the standard and the non-inferiority limit on the hazard ratio. Now, since we only know the values for median survival, we must use those values to calculate these exponential survival parameters. So to do this, we'll click on Assistance again and do Conversion between parameters. So for group 1, which is our new drug, we'll enter 10. And for group 2, which is our standard drug, we'll enter 12. So you can see nQuery automatically calculates all these values for you. So we find here that these values correspond to a hazard ratio no larger than 1.2, and that the exponential parameter for the standard treatment survival time, which is expressed in months, is 0.0578. So we'll copy these across to our tables. We click Copy. Let's paste it in here. And we select our hazard ratio, which we find to be no larger than 1.2 in here. Now, so our question was, if we enter 80% power here, what would our sample size be? So we enter 80% power, and nQuery automatically calculates our sample size. So what we have here is that for such a trial to have 80% power, we find that it's necessary to observe a total of 944 events. To obtain that number of events, we would require 843 patients per group if the alternative hypothesis that both tests have and standard have the same exponential parameter as that specified in the table were true. Now, if the null hypothesis was true and the test was inferior by the amount specified, the required number of events would be obtained with a somewhat smaller sample size, that is n equals 801. Now, as before, our next step is to do a sensitivity analysis. So for our sensitivity analysis for this, our question we want to ask is, what sample size would we get if we wish to increase the power? So we have 80% power here in the first column. So I'll do is edit column name. So our first column we had 80% power. So for our second column we're going to see it's 85% power. And so on. So we click OK to transfer our names across. So you can see here now our four columns are labeled 80% power, 85% power, 90% power, 95% power. So you copy and paste, keeping all our values constant, copy and paste these across. And we enter our values of power, so 85% power for the second column, 90% power for the third column, and 95% power. So you can see how the increase in power impacts the sample size. So the greater power required, the greater the sample size that is required. So what we can do a user specified plot of all these four columns. So you click here to do a user specified plot. So on our y-axis we'll have n per group. On the x-axis we'll have our non-inferiority limit on the hazard ratio. And we'll plot this from, we'll say 1.15 to 1.2. Yeah, I would say 1.35. So you can see from this plot, what this plot is showing is that using a non-inferiority limit of 1.3 will require less than half the number of patients than a non-inferiority limit of 1.2. However, such an non-inferiority limit would imply that median survival for the new drug would potentially be as low as 9.2 months would be acceptable. Okay, so that's our second example on using nQuery Advisor. Again, if you wish to generate a statement, you say we're happy with 80% power, you can generate a statement. So the statement here says, when the sample size in each group is 843 with a total number of events required of 944, a test of non-inferiority of the survival curve for the test group to the survival curve for the standard group with a 0.2025 one-sided significance level will have 80% power to reject the null hypothesis of non-inferiority. So again, if you want to keep this statement, just click Store. It stays down here to the bottom right. And once again, you can click File, Print, and you'll print what you like to a Word document. Okay, so we'll just take a quick 2-minute break there. Again, if anybody's any questions on anything which I've done here, or indeed on sample size in general, again, we'll be more than happy to answer any of your questions. So you can enter your questions on the text box on the right hand side. So let's give people a 2-minute break there now to input whatever questions they may have. Okay, we'll just start back there. We're just 1 or 2 questions in. One person is asking what the last row in the last table, what that corresponded to. Well, what that was saying is that if the null hypothesis was true and the test was inferior by the amount specified, the required number of events would be obtained with a somewhat smaller sample size. So that's what the last row corresponds to. Someone else is asking as well just about what hypothesis we were testing. Well, that last table was a test of the null hypothesis of inferiority versus the alternative hypothesis that the survival rates are the same in both groups. Okay, so if more questions, keep sending them in. We'd be more than delighted to answer any questions you have. And as I say, the questions are being answered in rotation. So if your question isn't answered during the webinar, we will get back to you within 24 hours with an answer to your question. So please keep sending in your questions. We're delighted to answer any questions that you may have. Okay, so nTerm. Well, nTerm was developed to provide sample size and calculations for group sequential trials. It uses the alpha spending function method of Lannan-Demetz and includes the spending functions from O'Brien and Fleming, Pokwok, Hang-Shi Dakani, as among others. So, group sequential trials. What are group sequential trials? Well, group sequential trials are used to facilitate the conduct of an interim analysis. And what they are is they're a trial in which the data are analysed after each patient's results become available, and the trial then continues until a clear benefit is seen in one of the comparison groups, or it is unlikely that any difference will emerge. Now, group sequential trials, they differ from the fixed period trials that nQuery conducts, in that data from the trial is analysed at one or more stages prior to the conclusion of the trial. So as a result of this, the alpha value applied at each analysis or look must be adjusted to preserve the overall type 1 error. So in effect what you're doing is you're spending some of your alpha at each look. Now the alpha values used at each look are calculated based upon the spending function chosen, the number of looks to be taken during the course of the trial, as well as the overall type 1 error rate. Well, what are the benefits of doing an interim analysis? Well, the first benefit is that clinical trials by their very nature are longitudinal, so it is practically impossible to recruit, enroll and randomize all the required subjects exactly at the same time. So subjects and their subsequent data are accumulated sequentially over time. So sometimes instead of using fixed period trial methodology, researchers find it necessary to employ a group sequential design with a number of planned interim analysis in a clinical trial. Now the next benefit is ethical. Well, in human and animal trials, it is essential that you monitor your results to ensure that the subjects are not exposed to unsafe or ineffective treatments. On the other hand, if a trial is showing a very positive result of overwhelming efficacy, and early stopping means that a new product can be brought to the market sooner, this will save time and money. Okay, just to show you an example of how the sample size is calculated for group sequential trials, we'll be using the nTerm software. So in this example, we're looking at a study is being carried out to compare 2-year survival after surgery for a brain tumor for patients treated with a new combination of chemotherapy and radiation versus those treated with standard methods. We will use nTerm here to figure out what sample size is required to have 90% power for comparing the two groups. The new therapy we consider markedly better if it increases survival by about 15% from 20 to 35%. So in this example, we're looking at a log rank test assuming proportional hazards. The standard method has 20% survival after 2 years, and the new method, as we say, is considered markedly better if it has 35% survival after 2 years. So we're looking at a two-sided test with a 5% level of significance. We look at 4 interim analysis, so it's a 6-monthly check. And we're using the O'Brien-Fleming spending function. So the question we want to know is what sample size is required to have 90% power? So we'll open up nTerm. So this is the nTerm interface. Now the test we need, we have a number of tests here at the top. The test we need is a survival test, so we click on the survival test. So there's a 5% significance level, so we enter 5% here. It's a two-sided test, so we enter 2. And the group 1 proportionate time 1 that's the 20%, so that's the standard method. And we're 35% here. So nTerm automatically calculates the hazard ratio for you. Now this is we're assuming for this test is proportional hazards. We select proportional hazards. And again, the question we have is what the sample size would correspond to 90% power, so we enter 90% here. We have 4 looks, enter 4. And max times 24. So you can see how this impacts the looks here at the bottom. Again, we're using the O'Brien-Fleming spending function, so we select O'Brien-Fleming for the spending function, and we will not truncate our bounds. So to calculate our sample size for this, you just simply click Run here for calculate required sample sizes for given power, and nTerm automatically calculates sample size to be 334 here, with 243 events. You also see nTerm fills out the boundaries graph here, so you can see our O'Brien-Fleming boundaries with an alpha of 5%, so you can see how our alpha is spent over time here. You can snap this back in here, down here. You can also see how nTerm fills out the looks here, so you can see how our alpha here is actually spent over time, so the incremental accumulates then to 5%. Also see how our power accumulates over time. So again, like before, the next step is, once we have done that, is to do a sensitivity analysis. So for our sensitivity analysis, we want to see if perhaps the new method did not increase by 15%, but also had different values. So what we do is you copy and paste here again, copy, paste. So here we'll say we put in 0.25, or so it's a 5% survival rate compared to the increase, compared to the standard method. Here we'll enter 0.3. So you can see how nTerm automatically calculates the hazard ratio for you each time. So again, you click run. Run for this guy. So you can see how the difference in the sample size. So you see here, for a very small effect size, once again the sample size is vastly different compared to when the effect size is a lot larger here. So once again, even for interim analysis, just like in fixed period analysis, when the effect size is very small, you need a very, very large sample size to be sure that you can see it to achieve significance. So when the effect size is very large, like it is here, the sample size is markedly smaller. So again here, what you do is you can do a plot for these 4 columns. So you see it's often a lot easier to see the relationship between power and sample size across the 4 by plotting them. So we plot these 4 sample sizes. So you can see at the bottom as well, it gives out the alpha spending values in the looks column table at the bottom. And also the spending function 4 is plotted here, the O'Brien-Fleming spending boundaries on the right hand side. So this is our plot of power versus sample size. So you can see here column 2, which is the column which had the very small effect size relative to the others, and which gave a very large total sample size. It's way out here, so you can see the sample size required to achieve 90% power is much, much greater than the others. So you see here column 4 here, the first column here, first column on the plot, had a very small and very large effect size, which required a very small sample size. So here you can easily see the relationship between power and sample size across different effect sizes. So again, once you have this, you can snap this in here. It's one of the benefits of using nTerm, you can snap and change, move things around as you need. So once you're happy again, which we'll say with our 0.35% or 15% difference, then you can look at your output statement here. The output statement is automatically generated for each column when you run it. So here our output statement says that a total sample size of at least 334, that is 243 events, is required to achieve 90% power to detect a hazard ratio of 1.533. It's using a two-sided log-rank test with a 5% significance level, assuming that the hazards are proportional. So these results assume that 4 sequential tests are made and the O'Brien-Fleming spending function is used to determine the test boundaries. So that's how you calculate sample size using the nTerm software, and that concludes our webinar today on sample size. So all I have to say is thank you very much for your patience and your time. And if you have any questions on anything I've done here, or indeed anything on sample size or sequential designs, then please do send in your questions, and we'll be very happy to answer. I have one question in there about what is the role for max times. Well, the max times is the total running time of the experiment. It is used to convert the time row in the looks table into fractions. So for today's example, I'll bring it back up there for you. So for today's example, I selected 4 for the number of looks, and I set the max times at 24. So this gave me 4 equally spaced looks of 6, 12, 18, and 24. These correspond to the 6 monthly checkups, which are as dictated in our study design. Okay, so if anybody else has any more questions, please send them in. I'd be delighted to answer them. And again, as we say, if your question is not answered during today's webinar, then we will get back to you within 24 hours. There's quite a large number of people attending today's webinar, and all our questions are being answered in rotation. So once again, thank you very much for your time and your patience. And if you have any questions, please do send them in. Also, if you have any questions after the webinar has ended, you can send your questions into support@statistical.ie. If you have any questions on today's webinar or on anything to do with sample size, we'd be delighted to answer any questions that you may have. Just for your own information as well there, we will be posting this webinar on our website, so if you have any, and this will be sent out to all attendees, the link to this website will be sent out to all attendees, so you can view the slides or on the webinar itself at any stage you want, it's just by clicking on this link. So it's time for one last question there. Someone is asking about to expand on using the alpha spending and the boundaries graph. Well, in the interim monitoring of clinical trials, multiple looks are taken at the accruing results. So in certain circumstances, it's akin to multiple testing, the alpha value at each look must be adjusted in order to preserve the overall type 1 error. So the alpha spending functions establish these adjusted alpha values for each interim monitoring point, given the overall alpha. Typically, they establish relative high alpha values for early looks and lower alpha values for later looks. Thus, they can constitute stopping boundaries, which, when crossed, indicate that statistical significance has been established. Okay, so once again, thank you very much, all of you, for your time. Again, if you have any questions on anything to do with today's webinar or on sample size, you can send them in now to support@statistical.ie. As I say, we'll get back to you quite quickly. So once again, on behalf of myself and Andrew, thank you very much for your time.